starting on page 13 in your packet. We'll begin with number 1. Natural log of x squared over 5x dx. Again, anytime that you see expressions combined through multiplication and division, we really have to treat this like one large rule. We can't pick and choose different rules to apply when multiplication and division is involved. So this is too messy for any one rule to handle. So you have to look to use substitution. We want to find the u value. So typically, it does take a little bit of kind of trial and error to find the u value, but usually it's either inside the parentheses or it's in the denominator. Those are most common 2 places to look for. Doesn't mean that it's always going to be the case, but if you see a set of parentheses, I usually like to just begin there and see where that takes us. So let's explore the fact that maybe the u value is natural log of x. We know the derivative of natural log of x is 1 over x, and that derivative should hopefully handle this denominator that we see here. So we'll see where that takes us. Okay, so if you can recall, the derivative for natural log of u is u prime over u. So du dx is just 1 over x. Cross multiply. Okay, so there's my replacement for dx. dx can be replaced with x du. And that x is encouraging because we should be able to get these x's to match and pair up. Let's see. Okay, I'll replace what I underlined in terms of u. Everything else I'll leave inside the problem. Okay, so just like what we wanted, we want the x to go away, and they do. And we should be able to clean up the coefficient or that leftover 5 to make it so that it will look exactly like a rule that we want to that's available to us. So that 5 can be pushed out in front as 1/5. And now that's just a nice clean power rule that we can apply. Right? Okay. So u squared becomes u cubed over 3 with the 1/5 that tags along. And then plus c. We pretty much have the answer. Just have to replace the u back in terms of the original variable x. And I can now write this. I can have this as 1/15 u cubed plus c. Replace u with natural log of x. Okay, any questions with 1? Two. All right, so too many terms in the denominator. We're not going to be able to rely on just power rule, but looks like use substitution. The denominator could be a good candidate because the degrees are exactly 1 higher. So we're hoping that when we find the derivative, we're going to be able to get some version of the numerator. At least the degrees tell us that's a possibility. So I mean, a lot of times it is just kind of taking your best hunch and moving forward and see where that takes you. Cross multiply, solve for dx. So our degrees match, but looks like our coefficients is not quite there yet in terms of canceling out. So what we want to do is we want to really think in terms of taking GCF, right? If we can get a factor going, we can't just pick and choose and say, okay, that's x cubed, x cubed. Remember, we can't cancel across addition or subtraction. So let's take out GCF and see if we can get a set of parentheses to match it perfectly here. So here, 3 terms here, GCF of, at least I can take out 7x, or at least I can take out 7. And here I can take out 4, right? See if that will get things to match up for us. And push that 7/4 out in front. All right, so this is nice, right? Take that 7/4 out, 1 over u du. We have natural log here. Any questions from within the first 3 steps here? Getting all that cleaned up nicely. Okay. Okay, replace the u back in terms of x. Okay, any question with 2? Okay, no question with 2? All right, here's number 3. All right, so first thing is, can we go through expansion? But there's too many terms in the denominator. Now, if the denominator was just one term, then I would go ahead and start thinking in terms of splitting up into individual fractions and handling each problem individually. But that x plus 2 kind of dampens that possibility. So next option is use substitution. Either the numerator or denominator, right? But the denominator is not going to be a good degree. This degree is so low that there's no chance of the derivative handling anything close to x to the 4th. And even if we let the numerator be the u value, we're not going to be able to create a derivative that's going to look anything like the denominator in terms of the variables involved. So this is one of those problems that it's going to be more of a long division, synthetic division setup. Synthetic division, long division has a very specific look to it. Rational functions, multiple terms, numerator and denominator. Okay, and the degree in the numerator higher than the denominator. Okay, so we can go through this using long division or synthetic division, but we're going to target synthetic division because the degree 1, x to the 1st power, allows us to be able to explore synthetic division. So even though long division can work, synthetic division is preferable. It just goes a little bit faster, a little less messy. Okay, so here are the steps with synthetic division. We're going to take that factor of x plus 2, find the solution. It's always going to be the opposite sign of what you see here. So put a -2 outside, set up half rectangle. And now we're going to put information from the numerator in our first row, but we're not going to put any variables here. We're just going to put coefficients. Okay, so every column is going to represent a degree. So we'll start with degree 4, coefficient of 1. Next up, we have degree 3. Degree 3 has a coefficient of 3. And then degree 2 has a coefficient of -1. But what's next? Okay, this is for degree 1st power, x to the 1st power. There's nothing here for x to the 1st power, but we need to have a placeholder for it. So we need to have a 0 for that x. And then finally the constant, the -5. Okay, any questions with the setup here? All right, so now we're going to bring, first thing we do is we bring the first number down below the line. And once the number is below the line, we're ready for it to involve multiplication. Okay, with a divisor a value out here. Okay, multiply, add, multiply, add, multiply, add, multiply, and add. Let me see. Yeah, +1, sorry. So this becomes -3. Let me change some of these numbers. Okay. Right, becomes 6. Add, multiply, and then -17. So if you don't get a 0 at the end, that means this is a remainder. There's something left over here. Doesn't divide out perfectly, but we can still set up the problem. Okay. Now this doesn't solve the problem for us. It just gets us to the starting point so that we can actually have a form that is easier for our integral rules to manage. So we have to assign new variables to these terms. Okay, we start off with x to the 4th, and because we're dividing by x to the 1st power, all of our degrees will fall by 1. So instead of x to the 4th, now my new degree is x to the third. Next up, x squared. Next up, x. Next up, constant. And finally, you have the remainder that cannot divide any further. So we indicate that over the divisor to indicate I can't divide any further. This is my leftover. Okay, so now once we're here, we still have to do our antiderivative. We haven't done any calculus yet. We just put it in an easier form to work with. So we still have to involve our integral here. So generally, it'll be pretty easy in terms of the first few terms. Every term that you see here are nicely separated, no attachment with multiplication or division. Everything is set up nicely for power rule. It's this last term, though, that we have to involve u substitution. So u substitution, the u values in the denominator. This is going to be a pretty straightforward natural log problem. So if you feel like you can jump directly from here to the natural log antiderivative, you can do that. Or you can go through u substitution, which I can show the steps there as well. So you kind of treat this like its own separate problem. All right, du dx equals 1. 17 over u times du. Pull the 17 out in front. Natural log of u. And so therefore 17 natural log absolute value of x plus 2. Okay, so if you're comfortable, some of you may be able to jump directly from here to here without having to go through all the notations, which is fine. Okay, so let's do power rule here. X to the 4th over 4. X cubed over 3. Squared over 2. 6x, and then minus my antiderivative of this expression. And don't forget plus c. Okay, any questions of 3? Okay, here's number 4. Okay, integral from 4 to 9, dx over square root of x times 1 plus square root of x. Okay. Make sure we understand that the bounds is always the last thing that we do. We never work with the bounds until the very end. There's too many terms in the denominator. We're not going to be able to expand. We really don't want to distribute this through. If we do, we kind of lose that possibility of finding the u value. So what's our u value here? Yeah, 1 plus root of x. I'm going to rewrite the problem, push that dx outside the fraction just so that it kind of looks more like the way that all the other problems are set up. You don't have to just. Okay, so we know we're going to target that 1 plus root x because the derivative should produce some radical that hopefully we'll handle with this one, right? We know that this is x to the 1/2, which derivative is not going to go away, right? It's going to be a leftover x after we go through that derivative. Okay. Going to get that u value ready for power rule. So rewrite that square root of x is x to the 1/2, and now I can go through power rule. 1 goes away, x to the 1/2 becomes 1/2 x to the negative 1/2. Yes, question?
How did you get x
We went through power rule. So power rule, we bring the one exponent down, and then we subtracted 1 from the exponent. Okay, so derivative power rule. Okay, get this cleaned up here. All right, just feels a little bit cleaner if I can just get all the negative exponents resolved. And then now I'm going to get that x to 1/2 back in terms of square root of x, just so I can get it to match what I want to cancel out a little bit later. You don't have to, but just visually, it just feels a little bit cleaner. Okay, cross multiply, right? We want to solve for dx. Hey.
Can you sign a form like first to get that?
I'm sorry?
Can you sign a form to me when you want to check that?
Yeah, sure. All right, so we make our replacements here. So I'm left with 1 over square root of x times u times 2 root x du. Okay, root x goes away, the 2 stays. Pull the 2 out in front. Okay, 2 depth integral of 1 over u du. This is a nice integral rule that we can apply, which we know is going to be just natural log, right? So we have 2 natural log absolute value of u. Okay, so now here you have 2 methods you can go about doing this. You can bring your u back in terms of x, and then use the original bounds, which is perfectly fine. I'm gonna show both methods. The other method is the other method is leaving the antiderivative in terms of u, and then converting the bounds so that the bounds are also in terms of u. So convert bounds. Okay, so if my lower bound of x is 4, then my conversion is going through this little equation here. One plus square root of x. If I plug 4 in, I get 1 plus square root of 4. That's 1 plus 2, which is 3. So my new upper bound, sorry, my new lower bound is now going to be 3 in terms of u, because I'm leaving my antiderivative in terms of u. And my original upper bound of 9, I'm going to get it in terms of the same variable as u, going through this process here. Square root of 9 is 3, 1 plus 3 is 4. So my now I have matching variables here. U, variable, and then my bounds are also in terms of u. So now I'm going to evaluate my bounds. Whatever starts as your lower bounds, 3 and 4. Yes, question?
Do we not have to do plus or minus on the?
No, we only do plus or minus if you have an equation. Like if I had like x squared equals 4, and if I'm trying to do take the square root of both sides of an equation, that's the only time that plus or minus shows up. Okay. All right, so whatever starts as your lower bound will end as your lower bound, regardless of whether there's any changes, whether there's a change in order. So when you go through this process, it really doesn't matter if your upper bound is a lower value. Okay, things will work itself out. Just go through the same process here, but we don't want to be flipping the bounds unless we want to manually do that. Okay, so whatever starts as a lower bound, you're going to have to keep as the lower bound. Whatever begins as the upper bound needs to end as the upper bound, even if these numbers end up flip-flopping. Okay, upper bound first. Minus, then lower bound. And here I can have the absolute value, but I can also drop it as well because 4 is no longer a variable. We don't have to protect that value from being a negative. So we have 2 natural log of 4 minus 2 natural log of 3. Just as a reminder of, this is perfectly fine, but just as a reminder that we could get this even more cleaned up in terms of representing using log properties. Remember, natural log of A minus natural log of B is just natural log of A over B. And then you can even clean up a little bit more by bringing the 2 up as an exponent. All right, so any of these options are fine. I just want to kind of show you because if it was on the AP exam, sometimes without a calculator, they may have their answer choice all the way down to here. And you may be looking at the right answer, just have to match it up, okay? So that's method 1. The other method is taking your antiderivative, bringing that u back in terms of x, and the other method is bringing the u back in terms of x, like you normally would. This is the method that I think many students prefer to use, which is fine. And then once you bring your u back in terms of x, then you're free to use the original bounds because the original bounds is also presented to us in terms of x. We should get the same answer. Okay. Upper bound in for x. Square root of 9 is just 3. And then plug in the 4 in for x. So I get 2 natural log of 4 minus 2 natural log of, this is root 4 is 2, 1 plus 2 is 3. So we get the same answer. Any variation is fine. Any method is fine. I think that the danger that I see students make is they get to this point and then they start using the 9 and 4. So we don't want to use a 9 and 4 with the u, right? Either you bring the u in terms of x or you convert the bounds in terms of u, but you don't want to be mismatching variables here. Okay, questions with 4? Okay, here's number 5. All right, indefinite integral, 2 cotangent 3x minus secant of 4x. So we have cotangent and secant. These are part of our new rules. So as a reminder here, cotangent of u, I like to think of cotangent as cosine over sine, and that helps me remember that it's the sine that shows up in my natural log rule. And then secant also involves natural log, but it has secant and tangent that shows up within its natural log rule. Okay, so, but there's a little bit extra going on here because both of these require a little bit of U substitution. We got to make sure that we keep track of the 3 and 4. But let me talk about the shortcut that you can make is that if your U value is a relatively easy, simple, linear expression, then the leftover that's coming out of it is always going to be the reciprocal of the derivative. So this 3 is just going to produce a what? 1/3 as the coefficient, and the 4 will just produce a 1/4. So you can use that shortcut to kind of avoid having to write out all the steps for U substitution, but you're welcome to do that as well if you like. Just wanted to offer that that shortcut if it works for you. But really, we need to treat this like 2 separate problems. Okay, if you want to go through the full U substitution process, I can go through those steps here. So treat this like 2 separate problems here. I'm going to target that 3x, target the dx here. Okay, so just like what we suspected, that 3 is going to be pushed out as 1/3. The 2 goes along with it, so we're left with 2/3 integral cotangent of U. Okay, from here, we can apply the integral rule for cotangent. All right, on the other side here, secant, if you want to go through the full U substitution, we can. But we know ultimately it's just going to be a 1/4 that's going to be pushed out in front. Right, that 4 in the denominator gets pushed out as 1/4. Okay, so we have 2 rules now that are ready for our antiderivative rule. Cotangent becomes natural log sine of U. 2/3, we'll just tag along. Now, we got to be careful, right? These 2 U values are different U values, right? This U value is for the 3x, this U value is for the 4x, right? 2 separate problems. I know we're using the same variable, but these are 2 separate processes. This natural log of U becomes natural log of 3x. There's a minus sign that comes after this first term, and then secant becomes natural log secant U plus tangent U. The 1/4 will tag along in front. Okay, remember this U is with 3x, and these U's are with 4x, right? All right, any questions with 5? Okay, here's number 6. If you're looking on your morning review, sorry, the copy came out a little grainy, so some of it you may have thought it looked like 7 to the x, but a 2 got cut off, so it should be 7 to the 2 over x squared dx. Okay. So we need to kind of recognize that, oh, this 7 is not just a 7, right? This 7 is inside this exponential function. This is base 7 raised to an exponent. We really are going to kind of have to take into account that there's exponential function base a involved. So if we're trying to target that a to the u rule, that kind of helps us identify what our u value could be, right? What could be our u value? Okay, this exponent, right? Okay, it doesn't seem like this exponent is going to do a whole lot of good to match up with this x squared, but that x is in the denominator, so when we find the derivative, it will actually work to get to match that x squared. Let's see how that happens here. So u equals 2 over x. Okay, I do want to get this ready for power rule. I prefer not to go through quotient rule, so I'm going to bring that x up to the top. Okay, so now this is nicely ready for power rule. So du dx, bring the exponent down, subtract 1 from the exponent. Do a little bit of cleanup, bring the exponent back down, and now I'm going to cross multiply. Solve for dx. Take your substitutions. Exponent with the u, dx with this. And you see that x squared showing up, right? That x squared will pair up nicely with this x squared here. All right, there's a leftover what? That would negative 1/2, right? We don't want to say negative 7/2, right? The 7 is not a coefficient. The 7 is stuck as an exponential function here. So really just a negative 1/2 that can come out. So now this is the a to the u rule. Okay, it feels a lot like e to the u. It's basically the function itself, but then there's a little bit extra because it's not base e, so there's a conversion that has to happen. So as a reminder, we're applying this rule here. A to the u du becomes, there's a little bit of a coefficient that has to stay in front, but then the rest of it is just the original function and then plus c. So, all right, so we're going to apply this rule here. The negative 1/2 is just going to hang out in front. There's a conversion that has to happen. So 1 over natural log of 7 into base e. And then the rest, 7 to the u plus c. Okay, coefficient, rule plus c. You can clean this any way you want. Just make sure that you bring your original 2 over x back into your answer. Yeah, so any rearrangement of this answer is fine as long as you have all the pieces there. All right, any questions? All right, see you guys in class.
I wasn't here Monday, Tuesday. Can I take it tomorrow? Can I get lunch or something?
Yeah, that's fine. And today, you want to just,
I have the
review?
homework to do.
Okay, that sounds good.
I have the homework from last week, but I just got to do Mondays.
Sounds good. All right, thanks.